Okay, good afternoon or good morning or good evening to everybody. So welcome to the MOX Colloquium. This afternoon, we have the privilege to host Professor Wolfgang Dahmen, a chair professor in mathematics at the University of South Carolina in Columbia, in the United States. Wolfgang received his PhD from the Technical University in Aachen in 1976, and afterward the habilitation from the University of Bonn. Actually, I remember when in 1975,
we
can
met
you hear
there.
me?
Yes, we met there in Bonn.
Exactly. In 75, I spent the first semester in Bonn. These are my first visit abroad, indeed. And we met at a computer center. I think that you did not, of course, know me, but I knew you. You're already very famous, even though you're so young at that time. So Wolfgang has held a professor positions at different universities in Germany before at the University of Bielefeld, and then the Free Universität in Berlin, and then he joined Aachen, the RWTH Aachen in 1992, and he has been there until 4 years ago when he moved to the US for his, let me say, for his second academic life. Wolfgang has received many awards and recognitions, and just for the sake of time, let me simply mention the Leibniz Award, the Keck Future Award at the US Academies, and the East Fellow. And he has been elected to the Leopoldina, which is the German National Academy of Sciences. His interest, his research interests are mostly in approximation theory, in numerical applied and harmonic analysis. And I'd say that the cornerstone of his scientific research achievements is the development and the analysis of nonlinear adaptivity with application in different fields. For instance, image analysis, data analysis, machine learning, more recently, the numerical solution of singular equations and partial differential equations, and the model order reductions. And among his very many impactful research papers, I'd like to mention those in compressed sensing, in wavelet and multi-scale methods for operator equations, in multi-level preconditioning, in about orthogonal spline wavelets, in the convergence analysis for greedy algorithms, in the reduced basis method. And today talks will be on some thoughts on PIN, physics in four neural networks. This is a very hot subject in numerical analysis PDEs. So Wolfgang, thank you very much for accepting our invitation, and the virtual floor is yours.
Thank you, Alfio, for that extremely generous introduction. But you notice you are stealing my time also by telling all these things. So I have to catch up now. Anyway, there is a word of warning. The title says some thoughts, and I mean it really. So I'm going to share my thoughts on this. So this also means I'm not going to flood you with any pictures. So let's see how far we can get in this. So let me first explain. Here's a quick overview of what I'm going to talk about. So I will explain the playground where we will exchange some thoughts. I will briefly touch on a very important ingredient from my perspective. And then I will turn to implications regarding the PIN, what appears in the title. So let's see. But I have to see. So here's the problem setting. We think of a physical model, say a family of parametric PDEs, and we abstractly write it in residual form. So F is a differential operator, the unknown is U, but the differential operator is actually a family. It depends on, and so on, it depends on some parameters Y, which could be high dimensional vectors. And this is what it says here. It says the dimensionality of that parameter domain here, we activate this. this dimensionality could be large, which of course causes a problem. Everyone is aware of this. The object of interest is what it's sometimes called, in particular in model order reduction context, it's a solution manifold. It's the collection of all the states you can get by traversing your parameter domain. So when Y changes, the PDE changes, you get another solution and you collect them. These are the U of Y. So the U of Y are actually have values in some function space. For each Y, you get a solution, which is not a number, but it's a solution to a PDE. Okay. So no, this is too far. So here's what you do. So of course, the exploration of such a solution manifold is at the core of a lot of applications. And it is in forward simulations where the question is, I give you a parameter and you quickly return to me an approximate solution that corresponds to that parameter. But maybe even more importantly, in inverse tasks, where you get some partial information about the states and you have to infer back to the point in the solution manifold. And that is referred to as state estimation or even parameter estimation, depending on. Can I get rid of this thing? This is too bad. Let me see. How do I get rid of this? Anyway, I hope I could do this. Now, the key objective behind what we are going to discuss is now to learn an efficient surrogate for that mapping that takes you from a parameter to the state. And this is relevant for both forward and inverse tasks. When I say learn, this really will boil down to the task of equivalently reformulating the PDE system as an optimization problem and then use machine learning type of methods. So this is what it's going to boil down to. Let me see. Now, the typical object that are nowadays very much on vogue in machine learning refers to the type of hypothesis classes in the natural jargon. So what are the ways how you formulate your estimators? And of course, deep networks play a very prominent role. And for what I'm going to discuss, it's not so, the technicalities of this are not so important. What is important is that they are compositions of mappings, each one in a simple form parameterized by a certain number of parameters, but they are composition of mappings. And in our case, these curly n will be always referring to some ansatz for an estimator or an object in a hypothesis class that depends on trainable parameters, theta. Always, these will be the trainable parameters. They are distributed over the different layers. So each layer has a collection of such, and the entity is referred to by theta. And the input parameters are spatial variables. This is this one. Spatial variables, they are sitting in a domain omega in low dimensions. And these are parametric variables. These are the variables that are sitting in our parameter domain. So this has dimension dx, say, this is small. This is either 1, 2, or 3, or 4, maybe. And this has large dimension. Dimension was this number dy, which could be large. Okay. Now, here is a typical approach. Learning means typically you boil down to minimizing some empirical risk. And there are quite a few papers, and I mentioned some of them here, down here, that do that. Among them, in a slightly different context, also by myself and my colleagues, Zhu Wang and Min Wang from the US. But in the simplest way, they just take samples of the solutions and formulate a mean square risk. So these are spatial samples, X, and parametric samples, and you form this humongous empirical risk. And then you try to minimize it over the parameters theta in our budget. In fact, if you want to be a little more careful, instead of doing necessarily a simple stochastic sampling in the spatial domain, you can try from the very beginning to minimize that empirical risk in a better norm. So this norm will depend, of course, on the PDE model. And it depends on the problem, but this is already a little bit better. But in the end, you still need a lot of snapshots. So this NY is typically going to be somewhat larger because this you can expect the Monte Carlo rate, and that doesn't decay very quickly. So you will need many questions, and that, of course, is already the difficulty because that's expensive. These snapshots should be accurate because otherwise you lose accuracy from the very beginning. And this is what PIN does. It avoids this by saying, I don't want to compute first these approximations and then fit them. I just want to minimize a residual risk. This is the type. So remember our PDE. Now I can't activate the pin. Our PDE was formulated in a residual form with an F depending on Y. So the solution should satisfy this. And therefore, the natural idea is to minimize something involving this object to drive it to zero. All right. And here is the simplest, straightforward way to do this. You just sample now the residual. Note, this is only evaluating a residual. It's not computing any approximate solution beforehand. It's evaluating this residual and then minimize over theta. And the appealing thing is you could even think of taking off the shelf, say, machine learning software to do this job. So it seems to offer even non-experts a great way into this business to doing such modeling. And of course, the main contributions come from Kaniadakis, Raisi, and co-workers. There are countless. Then more recently, Sid Mishra has done a lot of interesting work on this, again with different co-workers, and we'll get back to this quickly. So, but however, there is an issue, and we finally have to get to the thought part. Let's look at a specific example, namely the fruit fly in numerical analysis. Let's look at a parametric family of diffusion equations, or elliptic, second order elliptic, standard PDEs, where the parameter is sitting in the diffusion field. Okay, so this has been investigated countless number of times. Now, if you do this, if you apply this principle, this is what you do. So you simply take the residual and sample it at X and Y, and you enforce the boundary conditions by sampling on the boundary and add another penalty term, maybe weighted by some lambda, and then you go ahead. But there is a little bit of an issue. So you would say, if I sample many times, or I drive the sampling number to infinity, I should get a much better accuracy. But you see what happens here is this would tend to this kind of norm for the residual. And for the boundary terms, it would tend to an L2 norm on the boundary. But everybody knows that this may be an issue. Namely, this one is too strong. And this one is too weak. So what can you get? What can you expect in order to get some kind of reference back to the error you actually have in the relevant norm, which would be the H1 norm, because you typically want to control also fluxes. You generally do not get from the size of these risks any real bound on your error. So that's this predictability issue. The other thing is you may not even have in the limit a residual that lives in L2. It requires full elliptic regularity. And if your coefficients are piecewise, are discontinuous, then you will certainly not have that. In other words, you require excess regularity, and that is, in a way, a built-in instability, or it aggravates in the when dealing with inverse problems, it aggravates ill-posings. I had a recent paper with Rob Stevenson on data assimilation for parabolic problems, where we used variationally correct residuals at the expense of having to deal with a dual norm. But as a result, we get error estimates that are independent of a Tikhonov regularization parameter, while other papers who do not do that, but impose excess regularity, won't get this. So in inverse problems, this difference is actually highly aggravated. Okay, so that's the issue. So what's to do? So here is what I really would like to discuss. What would one have to do in order to actually ensure a prediction capability of such simulators? Because that's ultimately what a numerical simulation tool should be able to do in the end. And this has to do with how to assess accuracy. If you run your optimization, and in the end you have to say, what have I achieved? So that's a core issue. The second issue is, well, you can study all sorts of individual problems. Are there general mechanisms which one could follow in this? And the third thing is one has to take high parameter dimensionality into account, which makes in the states as functions of the spatial and parametric variables are functions of many variables, so there is an issue. And an interesting question to me is a priori analysis versus a posteriori accuracy bounds. Now, in the classical regime of numerical analysis, we get very, very far by excellent a priori estimates. They tell us the ballpark of the results. They also say what we can expect with high fidelity. They also provide us with predictions how expensive it is going to be to solve a problem. But if you look at a numerical scheme, it never uses excess regularity. A finite element method converges just in H1. It may converge slowly, but it does not depend on anything more than that. So in machine learning, and in particular when dealing with networks, this is completely different. There was a recent interesting paper by Gross and Vogtländer about the theory to practice gap. And that means if you use point samples as your source of information, and if your network has been proven theoretically to achieve a high order of convergence, you will not recover it. You will not recover it. So even if you have a priori analysis in expressivity powers, you say, oh, these networks, they can catch whatever classical method can do at the same accuracy. You are by no means ensured that your training algorithm will actually recover this. So you actually don't know what an a priori estimate means. So what else can you do? You can try to assess your accuracy along the way. And in fact, I claim it has a big implication on optimization strategies, actually. And hopefully we'll get to this. So wait a minute, maybe I go too far. This is okay. I was there. Okay, if I'm serious about assessing accuracy, I have to give a functional reference setting. In which functional setting are my states without requiring excess regularity, and in which reference metric should I measure accuracy? So the first question is, what is the space U that accommodates the solution manifold? Well, in many problems, this is straightforward. Like in the elliptic problem, this H10 in my little example of before. So U is typically given in a more or less straightforward way by the PDE. But then if we view U as a function of X and Y, there's the spatial variable, but there's this parametric variable. So it lives on omega times the parametric domain, say into R or whatsoever. Then what is the metric for that object? Okay, and this is all not very new. There are two prime candidates. Candidate number one is you measure accuracy with respect to the parametric variable in L infinity. And then you get this Bochner space, which is L infinity of functions that depend on y, but whose values are actually in U, which is the space that accommodates the solutions. And this is typically used in the analysis of reduced basis methods. The wrinkle with this is this works very well. In many applications, this is the right way to do. But from a theoretical point, the wrinkle is if y is a high-dimensional parameter domain, the rigorous results require monitoring errors over a high-dimensional domain. So that requires dense sampling sets, and that is fully subject to the curse of dimensionality. So you have to think about how to get around of this. So that's the wrinkle there. Now, therefore, taking this Bochner space, which is a little larger, which measures accuracy in the parametric domain as an L2, is much more in line with machine learning. It's more tolerant to high dimensions. Your Monte Carlo aspect sort of may at least give you something in high dimensions, where you are not necessarily covering, say, at a density of an entropy covering. So this suggests more a probabilistic model. So if you have a probability measure on y, which induces one on the solution manifold, then you can view your state as a conditional expectation. And so you look at the mean square minimization. This was exactly, and the empirical version of it is what we were looking at the very beginning, and it would require you to sample U, which again, we want to avoid. So now, but realizing that our states should be lying in U, so, and that the lifted states, the parametric version, they should be in this Bochner state. The question then is, what is a residual quantity which actually is equivalent to that error? If you want to measure accuracy, if you accept this as a relevant accuracy metric for your states, then you need a residual quantity that is equivalent to this. My acronym I like best is TER, like terror. It is terrifying. So it's a tight error residual relation. So that's our goal. And so in order to do that, I need a residual now that involves functions on the big domain, so on the high dimensional domain. So first, given this metric setting here, we have to see what this means. And that means we have to see what it means in variational terms. Okay, and yeah, there are some references to this. Maybe I move like this. So here, so in which sense do we say U as a function of x and y solves this residual equation? Well, let's go, and this is kind of important, so I go very slowly. So let's look at a parameter y. Then we have our PDE that depends on this parameter y. So now we take a weak formulation of that fiber problem, say, for each individual v. In other words, we view the residual as a function, which acts on a test function v. And let's focus on a linear problem where the y-dependent PDE is governed by a bilinear form. So then our residual actually takes this place. And where we have chosen some space V to test. Okay, so what? Now we want to cook up a similar problem on the lifted, in the lifted setting, in the parametric lifted setting. So now it's natural to take the test space, just the Bochner space, with respect to this V. Nicely, by the way, its dual is again a Bochner space with respect to L2. Only the dual of the V, the dual space of the test space is coming in here. So a natural lifted variation formulation that has appeared in many cases. So I just recall it in order to set the notation, is now this bilinear form where the y has disappeared because it's being integrated over. So this is all well defined now. Now we basically have a bilinear form on this pair of spaces, the parametric liftings. And now our guys as functions only of the parameters will be these conditioned expectations if and only if they solve this new problem, which now lives in this high dimensional spatial domain. And we will be using this notation all the time. Notice this bilinear form here, this induces an operator which acts on V. And therefore that operator takes U as an X. That operator takes X into Y prime because V is in Y, or it should do that. So this is the regime we have to we have to consider. And let me see whether I can do this. Yeah. So the question is, if I have made these choices, I haven't said anything about how V and U relate. If I've made these choices, does the residual measured now in Y prime, because this is where it lives, F is functional in Y prime, does this establish a tight error residual relationship? Can I use this quantity to measure, or can I train on this quantity to measure this? Is this valid? That's the first question. Well, most of you know it already. I just give you a gentle lead into it. This is well understood in numerical analysis. Let me try to advance this way. This is well understood, and and it gets me to what I like to call stable variational formulations. So this is what we discuss next as a building block in that whole procedure. And it goes back to the famous theorem by Babushka and Nechas. So we look at a pair of spaces, X and Y. These could be the lifted spaces we have discussed before, and we have a bilinear form on it. And there are essentially three crucial conditions, namely that bilinear form should be continuous. This is this one, with a continuity constant C, capital C. And it should satisfy an in-soup condition, which should be this one. That's the critical one. And there's a surjectivity condition. So these are the conditions in the famous Babushka-Nechas theorem. And they say this problem has a unique, and these are equivalent to the unique stable solvability of the variational problem behind this. And my claim is, it is actually equivalent to the fact that we have a tight error residual relationship. So remember, this is the residual here. It can be written as the right-hand side minus the operator application. So these conditions say that B mapping from X to Y prime is an isomorphism. This is what it says. In other words, errors and residuals are the same because F is, of course, B of U. And then we have B of U minus W. And since B is an isomorphism, we have this with my in-soup and continuity constants here. Okay, so this is the same. Saying I have a tight residual is the same as this Babushka theorem. And but before we go about, oops, I went one step too far. I should make a remark, namely, when is this valid? Well, in one direction is very easy, and this is enough for me for today. If the fiber problems are uniformly stable in that sense. So if the fiber bilinear form satisfy 4 uniformly in Y, then of course the lifted problem does so too. So we have to look at the parametric problems individually and then see how the parameters affect this. This is the task now for a specific problem. Now, a nice thing is if we have this situation, then whether we lift the problem to the continuous Bochner space with the full continuous parameter regime, or to a finite subset, which we always denote by this hat, white hat, which corresponds to the training situation. And the Bochner space is now a little L2 Bochner space. Doesn't matter, it doesn't give any difference. If we have this, then we have both simultaneously. So I use X and Y for both situations. And whenever there's a computation, it will be this version because we have finite samples. But the stability is not affected by this. So, but the question is, of course, this. We have this sandwich, this tight error residual relationship that relates errors to residuals, but the residuals live in a dual space. And that is typically not easy to evaluate. In fact, it is by definition a supremum over a full function space. So that's not computable the way it is. So if I do that, this would be a variationally correct reformulation of my PDE as an optimization problem, but it would be a min-max optimization. Okay, so how to deal with this? In many situations, one has done this in other contexts without maybe emphasizing this perspective. But let's look at a couple of problems. Two problems that should guide the discussion. We go back to our fruit fly. Of course, here's again the elliptic parametric problem. Now we know everything. The trial space U is H10, and the test space is the same because of ellipticity and because we have a symmetric variation formulation. Now U prime is H minus 1, and this should show up in the residual rather than L2 in order to avoid excess regularity. So in this case, X is this standard Bochner space. And there are similar formulations, even for space-time formulations, for parabolic problems, wave equation, Schrödinger equation. There are all sorts of scenarios that have been discussed in the literature where these pairs of stable spaces are known. And many times they have to be different. So you cannot get away by taking the same test space than the trial space. So it's typically not a Galerkin context what you are looking at for these maybe more challenging spaces. One example, an extreme example of this is linear transport. There's no dissipation, there's no stabilizing viscosity. You just have a convection field which depends on a parameter. Maybe you have a reaction term, it's not necessary here. And the first option to have a weak formulation of it, which we need in order to formulate our residual, as pointed out before, we needed this variational framework. Well, is just to take test functions, multiply this by test functions, and you could take just V equals L2. Very simple. Then the dual space is also L2, which is nice. However, your trial space now depends on Y, because you already have to build in essential boundary conditions depending on Y, because when Y changes, the direction of the convection changes, and so the inflow boundary conditions change. So, I mean, this is a critical thing. Now, even the trial space depends very much on the parameter. And if you do a discretization, you can jump out of it because this is a nasty space. It may have even discontinuities parallel to the convection field. So there is a second option. And that second option is sometimes called an ultra-weak formulation. I went too far. No, let me do it this way. And what is this? Now you just do integration by parts. After multiplying this by a test function, you do integration by parts. So you free the derivative from the first order. From the first order, let me see, I have to, here. There's no derivative anymore. Instead, the derivative now acts on V. And if you do that, of course, you get trace terms. And that's bad, because now you are looking at U in L2, but U in L2 doesn't have a trace. What saves you is, originally you would have a full boundary of the domain. But if you choose your test functions to vanish on the outflow boundary, you're only left with the inflow boundary. And if on the inflow boundary you have data, then you stick them in and you have a functional that belongs now to the right-hand side. So your boundary conditions become incidentally natural boundary conditions. From a machine learning point of view, that's nice because now they live in your variational residual, and you don't have to cook up something that's maybe variationally wrong, theoretically. Okay, so now the test functions have the derivatives and also some trouble maybe with the boundary conditions, but at least your functions now live in L2 and they can accommodate shear layers, they can accommodate discontinuities, all sorts of stuff. And there's lots of work where this is shown, this is all in soup stable. So some papers with Rob Stevenson, something with Christoph, another former postdoc of mine, and Gerrit Welter, and some recent work on radiative transfer, where this plays a big role. So this is to some extent understood. But you see here, it's very important which spaces you take. All right. One further. Don't move. Okay. Now, these were two examples, and you could wonder, well, is there a more general recipe for other problems? In fact, there is. So I'm not going to discuss any specific other, but I give you a hint at this kind of recipe. So we go back to our operator equation. So we are looking at at VU equals F, say. And we formulate it in this way, in the weak way, which usually gives, after integration by parts, a nice bilinear form. And once we do that, we can also formulate the dual operator. It's a dual operator. Abstractly, it's defined like this, but B mapped U into V prime, and B star now takes V into U prime. So if we just take this simple observation and do the following thought experiment, we define now the test space. We look at the closure of a dense set of functions under this operator B star, and provided that we have shown injectivity and surjectivity for such collections, we can go to the closure and define this as the norm. Because as a result, we will have that the in soup constant is easy to check. The in soup constant is 1, and the continuity constant is 1. With this metric, the operator becomes an isometry. So in other words, errors are not just tightly related to residuals, they are equal in size. Okay. Now, then of course you say, well, that is, you shot yourself into the foot, because now in that definition, you have a dual norm, which again, you can't compute in general exactly. So, but if your trial space is an L2 type space, product of L2 spaces, if you wish, it is self-dual. So you can replace this by U, which is an explicitly computable norm. And this is one advantage of the ultra-weak formulations. So in an ultra-weak formulation, this is exactly when this is the case. You can cook up a situation where you have nice error residual relationships. Okay, so no. Let me see, I went too far. Did I? Yeah. So here's the general recipe, of course. I mean, it's not that simple, but this is kind of a rule of thumb. You can try to reduce your system to first order equations, mixed formulations, then you move the derivatives to the test size using integration by parts, and then boundary conditions become natural ones, and you end up with a situation where you can compute the optimal test norm. This is often called, optimal test norm. Optimal because it induces an isometry. And this has been used even in the reduced basis method. There's this double greedy thing, which gives you a guaranteed performance like the Kolmogorov N-width, which uses exactly this. And it has been used by Carstensen, Demkowitz, and Gopalakrishnan to cook up these stable DPG schemes for a whole family, including Maxwell equation, wave equations, Schrödinger equations, and so on. They basically make use of this principle. No, but now you have to deal with, okay, so these were the preliminary observations. No, we are still there. So now we are in the preliminary observations. You finish the stable variation formulation. Suppose we have done our homework. Our PDE, we have located a pair U and V for our parametric PDEs. So we immediately get a lifted problem on X and Y, and we have a stable variation formulation. Now residuals and errors are equivalent, and solving the PDE is the same as finding the zero of this quantity. And this can be formulated as finding the infimum over the space X, which accommodates the solution, but the supremum over the test space. So it's a min-max optimization problem. In the context of machine learning, this has been used, and it has been used by Gang Bao and co-workers, however, for elliptic problems, but exactly the same idea. So, and they even have carried it to inverse problems with elliptic problems, including EIT. Then Chen and collaborators have used it for Friedrich systems. So they have used just the transformation to first order systems and then use their stable formulation, because you can have identify them as a so-called Friedrich system that ensures exactly this stability. Again, it's a subset of what one can do. So here, as I said, I just take this babushka Netja's point of view, and because it does cover some situations which are not in the Friedrich domain. But now, in order to solve this, or to make this usable for a machine learning context, you would have to, or for the right-hand side to be a real error metric, you would have to find, for a given approximation W, you would have to find the supremizer. So given a hypothesis class, where typically maybe containing networks, but not necessarily, it could be tensors, doesn't matter. And finding for a WV, to make that really equal to the norm, you would have to find the supremizer, which satisfies this. And this is, of course, practically impossible. You have to supremize over a full space. But acted is enough to find a near supremizer. A near supremizer, however, means that you, up to a constant, find a V star, which realizes this norm. If you do that, you are in business. But you can already see, to make this a certifiable method on the min-max optimization, then you would have to solve this problem. And if you realize to do that, then you have a tight error residual relationship. So how to find near supremizers? That's then the next question. How do you do that? Well, everybody in reduced basis methods knows what supremizers are. Namely, they are Rees lifts. In other words, the V star, that is the supremizer for this functional, is a Rees lift. It solves a variation problem, where this is the right-hand side, is a continuous functional. And, oh, by the way, this is bull, this is Z. Okay, for all Z. So it solves a variation problem. In fact, it solves an elliptic problem. So this is actually a benign problem, regardless of what the primal problem was. You always do a Rees lift, which is an elliptic problem. Now, how accurate do you have to solve the Rees lift? Remember, this is what we are targeting. So the question is, how accurately should we resolve that Rees lift? Before we do that, we observe that the solution of an elliptic problem is an energy minimizer, which is a nice thing to do. And in particular for networks, energy minimization takes place in automatically the right space. So there's no worry of having a variational wrong formulation. So that Rees lift would minimize this function. All right. So, and then a little calculation shows that the required condition on that Rees lift is to achieve relative accuracy. And that sounds little at the beginning, but it is a tough condition because the residuals in the end will become small. And then this relative accuracy will become better and better. And if you do not achieve that, your training will give you crap. And this is being observed. And so it is a demanding problem. So let me now talk about two avenues one can take from here. So let me just quickly recap. So all I've done so far is I used the notion of stable variation formulation to cook up an objective functional for an optimization problem, which equivalently gives me the solution of the parametric PDE. Not only that, the residuals which I create in that minimization at each stage give me a tight error residual relationship. In other words, the size of that residual will give you the accuracy you have achieved. And this is something in an optimization where you are not sure whether it will succeed in finding your ideal optimum. This is important. So the first avenue is to use this kind of min-max optimization. In other words, but now how do you do it practically? And this is very reminiscent of what's called by the computer scientists generative adversarial networks, where they have a generative network, which is supposed to create your pictures. And there's an adversarial network or a discriminator that makes sure that you do not train on the wrong information. And in our case, that discriminator here is supposed to be an approximation to the Rees lift, while this is going to approximate you. Okay, so now how do you do it? You reserve a budget for your discriminator and you reserve a budget for your generator, and then you try to solve this min-su problem. And this has been done by these people I mentioned before, and also in the Friedrich system. And you observe difficulties for good reasons, because a min-max problem is always a little delicate. And it's, of course, it's already here clear. If your budget for the discriminator is not rich enough, you will never get near the Rees lift, and you will never be able perhaps to realize relative accuracy, which we saw before is what you really need. So it has difficulties, but I would like to discuss a little bit of it because it leads to interesting things. There's a second strategy, which I call a hybrid strategy, and it uses auxiliary meshes, and it uses the concept of DPG, discontinuous pattern of Colloquia. And I hope I get to this because that's, in my opinion, the more interesting thing to do. And if in discussing this, one already sees some implications in optimization strategies and regularization. Okay, let's see. So here is first the GAN, the generative adversarial network approach. So here's my take on this, and we have been successful with this with adaptive wavelet methods. Well, what did we do with adaptive wavelet methods? We contrived an idealized iteration scheme in infinite dimensions, and then we realized this scheme approximately within suitably chosen target accuracies. And then you can prove optimality and everything you wish. So what would that be here? I first tried to contrive an idealized optimization scheme in infinite dimensions. So at this point, I'm still, this has to go. Okay. So, but this min-max problem, I would like to reformulate it using Lagrange multipliers. Namely, I minimize over V, which in fact is the Rees lift. Because I would like to minimize the Rees lift of this functional, because it has the same norm. In Y, the norm of the Rees lift is the same as the norm of the functional f of W in Y prime. So I want to minimize the Rees lift. And I apply this condition that this guy is the Rees lift by Lagrange multipliers. This is this. We'll see what it means. So it actually says that the Lagrange multiplier Z star agrees with V prime, which is the Rees lift. So ideally. So I'm not doing something completely wrong. So the associated dual problem is obtained by solving first the minimization problem, so pulling that inside, and then supramize over the dual problem. So what this is, if you minimize over VW, which are the primal variables, if you do that, the V moves in, and you can solve this minimization problem because we have already seen the V and the Z is the same, and we end up with this. So that is the dual objective. So now we can cook up a scheme which is a kind of a primal dual scheme. Suppose we have some initial gases or some gases computed along the way. We do a gradient descent on the primal variable W, because that will reduce this functional, which stands for the residual norm. If ZK would be the reslift of this functional, this would be exactly the norm. And after doing this, we go right there, we do a gradient ascent on the dual problem to get close to the Lagrange multiplier. But if you continue, but this is the same as minimizing an energy. So the Lagrange multiplier results from minimizing an energy, which is something that is fairly stable, even with networks. You have to cook up, you have to do these steps repeatedly, because one step will almost never suffice to give you a stable scheme. So you need some kind of a criterion to block. Let me sweep over it in favor of time, because I would like to get to a different point of view. In this, the gradient descent on W is actually, you actually minimize only on this one here. And that you can compute, actually, that direction you can compute. It's a reslift of the dual operator applied to the current Lagrange multiplier. Now, if you are in an ultra-weak formulation, then X, the reslift, is the identity, and you have it. You have the ideal descent direction. And now, if you think in terms of order encoders, or you would, in order to emulate such a step within some controllable accuracy, what you could do is just to approximate with a neural network this object, which is given to you, because W is a current approximation. So you could do that, and you could do it in a norm which is actually compliant with the metric, because X is now an L2 type norm. So theoretically, this looks extremely appealing. And as I said, in practice, this should be done by doing these steps approximately with suitable tolerances. Why is this appealing? Because the original objectives in this approach are very benign. These are just something happened here. You still see the screen? Okay.
Yes.
Okay. Good. So they are very benign. These are convex functions. Everything is fine and dandy. The only difficulty with the optimization is because you stick in for the W in your realization a neural network, which is highly nonlinear, and what you then have to work on is a highly non-convex problem. So the idea is really, as in that adaptive wavelet method, is follow the natural gradient flow that comes from these energies, from these convex functions. And that already indicates what you need to do. Namely, in order to be able to ensure closeness to the reslift, you probably have to expand the dual network, so the discriminator, even if you freeze the primal one and reserve a fixed budget there. But then the idea would be, in your expansion, you follow a natural gradient flow. This is currently under investigation. We have some promising results in this regard, but for a problem like this, we haven't completely realized it yet. But it does open a few interesting perspectives. So can this work? As I said, the adversarial network has to be close to a reslift for the current residual. Otherwise, you get crap. Otherwise, you train the network on a functional which has nothing to do with your error. And you can see this in experiments. So you may have to think about good ways of expanding or adapting networks. As I said before, the only problem is self-inflicted because you insist on using these highly nonlinear stuff. If you used linear ansatz, then of course that would be much more nice, but then you couldn't deal with high dimensions. So there's both sides of the coin. And as I said, there's a little bit of ongoing work, which is not mature enough to do use of this infinite dimensional setting so that you can use natural gradient flows that come from those functionals. Here is just one chart that shows that it may actually help to adapt, that you do not fix a priori a fixed network, but you adapt. And we made these experiments for ResNet structures, where each time you approximate a new layer and you do approximate a current residual, so to speak. And then we pose the question, if we train super long and see what we can get with a certain complexity, what is the effort needed to achieve, say, 9/10 of the final accuracy? And then the blockwise training, where you just expand gradually the network, each time actually optimize only over a single block, has the by far best performance. So this is something we would like to use in this context. So if I have a couple of minutes, let me give you an alternative, which I think is more interesting, because it doesn't have these, it may not have these delicate issues of the min-max formulation, where you are forced in each maximization to be good enough in order to train on a real error, instead of something else that allows the network to avoid into a corner where you really don't want to have it, just in favor of reducing this f of w. Anyway, this is based on another methodology that has been developed in recent years. I've been a little bit part of it, and I'm not the main propagator. Is Leszek, Demkowicz, and J. Gopalakrishna. But here's the idea. So suppose you have a variation formulation. This is this problem in variation formulation. This is what we had before. Now you create another variation formulation which is mesh dependent. So this is still an infinite dimensional problem. And in fact, for regular solutions where the solution is regular enough for both variations, they will be the same for each mesh actually. But it introduces another degree of freedom, which is being used for the following reason. Is being used to deal with Petrov-Galerkin situations, because in a Petrov-Galerkin scheme, it's not clear at all what to take as a test space. It's not just Galerkin where the test space and the trial space are the same. So sometimes the test space as a set is completely different, so that Galerkin wouldn't even make sense. And so here's what you do: you decompose this variation in variation formulation as an element-wise, where each BK now involves a bulk term, which is that cell K in the mesh, as well as a boundary term on the skeleton. So you notice I'm now using capital U instead of little u. This is because you have, in order to analyze this, you have to formulate this first in function space. In other words, you have to make sense, give sense to the traces. You have to create a space that accommodates the traces, because if you do an ultra weak formulation, you will be in L2, it doesn't have traces. So there will be a trace component, which in case of a regular solution, will reproduce the traces of the exact solution in the limit. Okay, so if my original, and so the point is my test space now lives on a Wagner space again, but the point is the test space is now as a broken space. The test space is a product of individual spaces attached to each element. So if you have a mesh, on each element there is a test space. And again, the meaning of this capital U, it has two. The bulk component is a function that lives on the cell, and a skeleton component which lives on the skeleton, which I sometimes called DT of the mesh. And usually you have to find the right norm, but there's a mechanism how to do that. And in all these cases I mentioned before, this has been done, and there exist these scalable schemes, which are more expensive, but they give you stability where the conventional methods do not give you stability. Okay, if you do that homework well, and this is not a talk about DPG now, but if you do these things all right, then you get in that mesh dependence space and in the corresponding Bochner space, then you get a tight arrow residual relationship where now, because of the test space is broken, you have a sum of local terms. So these are like arrow indicators. And unlike arrow indicators for elliptic problems, you can stick anything in your test space in there. This is a valid relation. Again, the wrinkle is they still involve dual spaces. They live on small cells, but they involve dual spaces. And the whole point in DPG is if you restrict the input to a piecewise polynomial in space, then these dual spaces can be reduced to dual spaces of finite dimensions. And then they become computable. And the amount of computation per cell is big O of 1. This big O could be big, but it's big O of 1. It scales like the number of cells. So in our case, the piecewise polynomials in space would be these guys. They would have coefficients that depend on y, on the parameters, but they would have functions depending only on x. And they are chosen in agreement with the DPG scale. And when doing this, you can prove for a wide range of problems that these local arrow terms, as long as you restrict them to functions in that finite dimensional space in xt delta, then they are computable. They become terms that you can explicitly compute and on which you can do adaptivity. So that's the big advantage of that DPG stuff. You only get this rigorously because you take the pain of analyzing the problem first in infinite dimensions and cook up the right norms, and then you can find this. All right, so now these guys you can compute actually for every input which you can evaluate at, say, quadrature points. So you can compute them also for non-discrete guys. Only if you do that, this error equivalence will no longer hold. But it can still be used as follows. And this is the key idea. What you can prove is that, now the idea is, of course, I will stick in here for the W, not a function that in the spatial variable is a polynomial, a piecewise polynomial, but a neural network, which of course doesn't fall into this class. The neural network is not in this discretized class. But nevertheless, I claim this arrow created by a neural network is still equivalent to these computable arrow terms, which I collect in this boldface guy, provided, however, something, namely that my current network approximation here can be well approximated by guys in this space, which are piecewise polynomials in space. These are those. So they are piecewise polynomial in space with coefficients that depend on y. So if my neural network that is approximate that solution of the DPG problem is close enough to such a guy, then this is a valid error estimator. And that only uses the stability of the problem, which I've established before. It's actually not so hard to do. But now, what does it buy us? Well, I claim this suggests a scheme. And this is maybe the main thing. So let me now look at guys which are piecewise polynomials in X. And I have to parameterize them now if I want to write them as also functions of Y. And the natural thing to do is that my original coefficients, Ci of Y, are now networks. And each of those can be approximated by some budget, Psi I. And these are all collected in the big psi budget for those values. And then you can do the following. First, for a coarse triangulation and moderate budgets, you can compute a guy of this type, for which these computable residuals are rigorous error terms, which minimizes these rigorous error terms. Okay. Suppose now you have done this for a couple of times for k larger than or equal to 0. Now you can solve, you can train your networks on a different problem. I mean, you find network parameters, theta, so that minimize this objective. This objective, now you stick formally the network into these residual error estimators because you can evaluate them. But at the same time, you force your network to be close to a piecewise polynomial, the one you have previously computed. And then you go on. Now, in order to this to be a valid error estimator, you have to make sure that this is small enough and that this term dominates this term. So here is where an adaptation comes into place. In fact, this is now a fixed function here for a given theta. It's a fixed function, and you can refine the mesh until this function, this piecewise polynomial space, will be a good approximation to your fixed function, and this will occur. At the same time, you may have to inflate the budget for your coefficient networks, but eventually you will. And as soon as you do that, you have a valid error estimator. And then you can check whether your current valid error estimator is smaller than your set tolerance, and you are done. So that is a scheme. In other words, it uses as a tool these kind of mesh-dependent empirical risks, which are, however, then rigorously founded, and incidentally give you an adaptation of the spatial domain. So it's not just a random choice of X samples in omega, but of course you can look at these local error terms because it's a sum of local terms and see where best to refine your mesh in order to eventually update this one here. So we are not completely, this is of course a little elaborate to do, but what would it get you? In the end, if you stop here, you basically have created a term that faithfully reflects the error incurred by your network in this discrete Bochner space, because the computation are here in that discrete Bochner space. Now, the question is, of course, how does this relate to what you're really interested in, namely the error in the continuous Bochner space? But the point is, this is something where you can tap into classical machine learning content, because that relates the number of samples to the continuous risk, how the empirical risk differs from the continuous risk. And of course, that involves now questions like, what is the complexity of the solution manifold? What are covering numbers? Or what is the VC dimension of the networks you are currently using, and so on and so on. But in principle, this is a separate step which you could adjoin to this one. And of course, it doesn't make sense to have 1 million samples here if your epsilon is a very poor accuracy, but it also doesn't make sense to have only 10 samples here and epsilon is 1/1,000,000. So there's a natural way of balancing these. So I think it's one good way to look at this is that forcing the networks as functions of X, because these are functions of X and Y, these are the input variables, they are actually close to piecewise polynomials in X. Is kind of a regularization that certainly keeps them from veering off. A network adaptation in either way doesn't seem to be avoidable. In the GAN approach, you will have to do it in order to catch the Rees lift. In this one, you basically also have to do it in order to actually enforce your regularizer. But overall, it suggests the nested iteration optimization strategy where you move from coarser to finer levels in a systematic fashion. There's a quick remark, maybe I skipped this. If you have quasi-interpolants for your spatial space UT, then like the Scott-Chung quasi-interpolant, then things are even easier because they are like the best approximation. And in that adaptation step where you get closer, where you approximate n by a piecewise polynomial in space, you can use these quasi-interpolants. And that will certainly, you don't have to optimize their parameters because you create, these are the CY now, they are coming from applying the functionals to your input. So that would simplify that, but these quasi-interpolants may not be easy to construct depending on what space you are working in. If it's a very anisotropic space, like with pure transport, you may have problems to realize such quasi-interpolants in the strong form. Anyway, it's another lead. But the point is, there is an automatic adaptation of the spatial sampling rather than just using something heuristic or stochastic even in a spatial domain. So the last section is there free lunch? And my claim is, of course, there's no free lunch. So the question is, when is this worth the effort? And for instance, you may be tempted to use this if you forget about the parameters y, since you only work on a residual, you could use it as a solver. And this is actually done by Kaniadakis and co-workers and by all the others. The primary effort is actually not into this kind of model reduction for parametric problems, but to solvers. I personally have a question mark. I'm happy to discuss this with you, but I have a very strong question mark on this, because you can see that in order to really ensure some kind of rigorous accuracy assessment, you really have to invest something. If your solution manifold is such that the Kolmogorov n-widths decay very quickly, that means objects can be approximated by linear spaces very well. I think in those comparisons we have done, the reduced basis type estimators are actually much more efficient and more accurate. The problem is you have to deal with this at infinity control over high dimensional parameter domains, but there's a probabilistic version you can do, which however is only valid under additional assumptions. So this is debatable. There is a regime, however, where it may, well, where it may be actually worth doing all this. And again, the extreme example is parametric transport, as simple as this is as a problem. Because then the solution, the Kolmogorov widths will not decay very quickly. You will have, just by sweeping over domains with corners, you will induce non-smoothness in the parameter dependence so that the linear spaces will not do a good job. However, one can show, and this is, I have to say, in preparation, so I don't think this is a very final, I think I can slightly improve on it, but you can show something like this. To achieve of that solution field U as a function of X, T also, and now the domain is a space-time domain, and Y, to achieve an overall L2 accuracy, which is a reasonable space for the ultra-weak formulation, then the network complexity is not subject to the curse of dimensionality. In fact, the network complexity grows with epsilon to the minus. This is just a spatial dimension. This is 1, 2, or 3. 1 is the time dimension. And the parameter dimension comes in only polynomially. So the space-time dimension. And then there are some log terms. So at least there is no exponential dependence on dy. So one may have a chance to use these kind of nonlinear surrogates for the solution manifold in such a case, which makes it worth it. Thank you. I probably went over time. Sorry for that.
Thank you, Wolfgang. Very, very, very interesting talk. Very interesting thoughts and remarks on such an important topic. So the floor is open for questions. If there are questions, you can open your mic and ask directly. And meanwhile, maybe I'm asking a question. Is there any way to use your adaptive error estimators to infer criteria for choosing the training set, at least in some special cases?
That's a very good point. I mean, for choosing the Y parameters also. Is that what you're saying?
Yeah.
The X parameters, yes, that was this mesh dependent thing.
Yeah.
Okay. So I think that's a faithful thing. By the way, I swept this under the rug too. When you compute a U norm, there's a quadrature behind it, of course. So there's always an additional consistency error, which I didn't want to. This is something more subject to classical numerical analysis. So, but for the Y dependence, the standard way, which is most often done, is just you do random sampling. So if you don't know anything about a law on your manifold, you use the uniform, the uniform law. But that gives you possibly only these very poor rates. There are these ideas about condition sampling. There is this weighted sampling that was recently studied by Albert and co-workers, which may give you a somewhat better placement in the parameter domain. And I think there's a good chance to use this, which I haven't looked into it because of the following reason. I will always be training on a residual term, which is equivalent to that error. In other words, it's comparable to exactly the situation that you have an L2 approximation. Eventually, you are computing in an L2 metric because U minus the network is in a mean square metric with respect to the parameters. You evaluate the samples as a norm of another space, but it's an L2 sampling. So I think these results should therefore apply, and they may be worth it in high dimensions. That's right. Yeah.
Thank you. So there's a question by Marco. Marco, you want to ask directly, or you want me to read?
Hi, Marco.
Hi, Wolfgang. I was wondering, how do you dynamically modify the architecture of the neural network in the first approach that you presented?
Very good question. This is not completely finalized, but I have this figure I showed you was sort of the simplest version of doing this. Let me see. I can go back to this. Yeah, maybe here. Okay. So here we used a ResNet. So by the way, that was an extensive empirical test. And for the situations we were applying it to, that was in state estimation actually, so it's a different regime. We found that the accuracy for a constant width 20 as opposed to a width 200 in the network didn't give you any difference. So width 200 turned out to be an extreme overparameterization, which you by far make up for by increasing the depth somewhat. And then what we did is we first created a coarse approximation with just one block, one layer in a ResNet. Iterated this fairly hard, and then successively in these loops here, enlarged it by investing another block. Of course, it's a ResNet block, so the initialization is very small. And that turned out to be the most effective way to drive that residual down. So that's the simplest. However, what I said, there is something in the cooking with this natural gradient or Wasserstein gradient. So here we take the point of view we really want to descend in an energy, like in this one, right? And the natural gradient flow for this energy would give you a predictable fast descent to the unique minimum. The only thing that is in your way is that the objects you do the minimization on is now on linear. But if you do the lookout for the next descent direction and allow the network to sort of adapt to this lookout somewhat, I can't give you the details, then there seem to be ways of incorporating this, this natural gradient idea into this network expansion, actually. Computationally, this would be extremely heavy if you compute a Wasserstein flow on the full network. But these experiments show that if we do only block optimization, in other words, we freeze all other blocks and only optimize on one block, it gives even better results because it's a much more stable situation. One shallow network is close to a linear situation. And computing, so the idea is then to compute these Wasserstein flows on each block, each residual block, okay? And but that is not implemented, fully implemented yet. There are only toy examples for this, so I can't, it's too early.
Thank you very much.
But it's part of the game. Unfortunately, this is all very intertwined. This is all very intertwined. You can't really separate one of those things, yeah. Thank you.
All right.
Thanks.
So I think I don't see any further request of questions. If this is the case, Wolfgang, thank you very much again. This was a very inspiring talk.
I apologize. Somebody has to stop me in these things.
No, that's fine. I mean,
look at the watch.
As very often happens with your talks, the very best comes at the very end, right? So it's a kind of exponentially increasing, interesting talk. Thanks a lot. Indeed.
Thank you.
All the best.
It was good. It was good seeing you guys. Take care. I stopped sharing now, so I give it back to you.
Thank you.
All right.
Bye.
Take care. Have a good rest of the day. Sorry for all you guys to keep you there.
No, that's fine. I love it. Thank you. Bye, Wolfgang.
Ciao.
Ciao.